In this video, I'll walk through an example very similar to the 16-1, just with some different numbers, and then talk a little bit through the rest of them as well and what you'll need to do to solve these problems. So we're going to start off with all of them with drawing a scatter diagram, and then we can look at that and see if the data appears to be linearly related or not. So when you come into Excel, you'll have your two variables. You'll have your x variable, which is called the independent variable, and then you'll have your y variable, which is the dependent. Basically, the x variable is the one that's causing the change, or we're viewing it as the driving force behind the relationship here. So in problem 1 here, the more money we spend on advertising, we expect higher sales. So X here is driving the change because the more we spend, the more we hope to get back in sales. So to see a scatter diagram, select all your data. Then go to Insert, and there's a little picture up here that looks like a bunch of points just scattered around. So you want that, it says scatter, and just click that first one, and you get your scatter diagram drawn here. So it has all the X values along the bottom, and the Y values, and you can kind of see where all these points fit if they're graphed out. Now this does, again, these numbers are different than what you'll have in your problem. I've changed them a little bit, but from my example here, it does seem to be a linear relationship. The higher up we get in X, the further along we get this way, the Y values tend to be getting higher as well, corresponding. Higher X's are resulting in higher Y's, which is what you would expect. The more you spend, the more you get back in sales. Now we can actually, so that's part A. Do you think there's a linear relationship, and is it positive or negative? That would be positive, because as X is increasing, Y is increasing as well. That's a positive relationship. If these were going downward, if as X was getting bigger, Y was going downward, that would be a negative relationship. So what's the least squares line? Well, what we want to do to find that is just click on our dots here, and you can right click and hit add the trend line. And my Excel opens it up over here. We're trying to add a linear line, and you want to display the equation. Go ahead and do that. I'll close out the settings there and move back. And so it kind of puts it right in the middle. You can drag it up so you can read it easier. So what is the least squares line? You just want to type in whatever you get back here. Might even let you copy and paste. My least squares line is this. That's the equation of this line. And what it's used for then is you can predict what the sales will be. You can predict what the Y will be for any given value of X, any given amount of advertising money spent. So let's say your company wants to know, well, how much should we expect in sales if we spend 80,000? Well, you plug 80 in, and whatever that value for 80 is in the line is what this equation will give back. So you do 80 times that number plus that, and it gives you what to expect back based on the data we have. All right, and so looking at what we want to do here, we calculated the least squares line. We want to interpret the coefficients. So first of all, let's interpret the slope here. The coefficient there is 1.752. Now, slope always means the same thing, whether we're in stats class or math class or econ or a business. Slope's always showing you how much something's changing in the y direction when we change 1 unit in the x direction. So for every increase in our x variable, which is advertising, so I would say, I don't know if this is going to show up right. No, it covered it up. But for every increase in, I could type it in here, for every increase in advertising by 1, which in our case, these are in thousands of dollars. So by $1,000, we expect Y, we expect our sales to increase by whatever the value of the slope is, 1.752. So the number in front of X is the slope, and this is always how you interpret slope. For every increase in our X value, advertising by 1, we expect our sales, our y value, to increase by what the slope is. All right, so that's good news if you're a company. You spend $1,000, you expect your sales to go up $1,752. Now, what's the y-intercept? That would be when x is 0. So if you spent $0 on advertising, you would expect to get that much back in sales. We always want to be cautious interpreting that. Sometimes it makes sense. In this case, it kind of does make sense for x to be 0 because it's possible for a business to spend 0 on advertising. So that makes sense. But always pay attention to this. If x equals 0 is outside of our range in data, then it really has no practical meaning. We don't want to use this equation for anything outside of our range of data. And our data goes from around 20 to up around 100. So we wouldn't want to use this equation to predict our sales revenue for something below 20 or something over 100. We would use it for values in between 20 and 100. So because our intercept x equals 0 is outside of our range of data, it has no practical meaning. Part C, determine the standard error of estimate. There's a formula in Excel that'll do that for us. So we just type standard error, STE, and we're using it between y and x. Then you select your y values, you hit comma, select your x values, and when you close out the parentheses, this is our standard error of estimate. Now what that is used for is part D, which says, is there evidence of a linear relationship between our x and our y, between our advertising and our sales? So we're going to compare that to the value of the y. So if I did equals average, and I'm off the screen here, but I'm just selecting my y's. I just selected my y's. Then when I close my parentheses out, this is the average of our y's. And if our standard error right here is relatively small compared to the average, then there is evidence of a linear relationship. And I mean, it's definitely smaller than it, so it is for sure relatively small compared to the average. It's about 10 times smaller. So there is evidence of a linear relationship between the amount you spend and how much you get in sales. And I'm actually going to ask you guys just to skip E. That's not something I want us to cover. But then going on to F here, predict with 90% confidence the sales when the advertising budget is $90,000. All right, so here's where we're actually going to use that line we calculated back in part A, right here, to make some predictions. So the first thing you want to do is plug 90 into that line to get our estimate, our one number value for what we estimate the sales is going to be. And that is going to go right in the middle of our confidence interval. And so just plug 90 in here for x. You're getting that value on your chart. For when x is 90, where is the line at? What's the value of that line that we're using for predictions? So I put 90 in there to the equation, hit enter, and there is my point estimate that's going to be right in the middle of my confidence interval. The next thing we need is our critical value associated with 90% confidence. T-distribution.inverse.2t, we want there to be 10% in the two tails. So because we're 90% confident, that means there's 10% in the tails. And so that's what we enter into our formula. And then I'm going to type 10 here, which is n minus 2. So whatever, you can see I have 12 pieces of data. 12 minus 2 gives me 10. So you type that in, and Excel gives you back your critical value. A couple other things we're going to need to calculate. We need the variation of our sample here from our x values. So I select my x values. So var.s for sample, select your x values, and you get that. And then I need the average of my x values. So average, once again, I'm going to select my x values over here. And when I close out my parentheses, there's the average of my x values. And then here's the equation you're going to want to use to get your margin of error. And we have all these values, so I know it looks complex here, but we already have all the numbers. We just got to plug it in. So this is on page 269, or right at the beginning of 16.5 if you're in the ebook, look for the part about predicting a particular value for Y, in this case our sales, when we have a given value of X for how much we're doing advertising. So I'm going to do all this. My critical value multiplied by that standard error value, and then multiplied by that entire square root. All right, so I put it there so we can be reminded of what it is. We want that critical value that we already found here. So P25, we found that. Multiply that by our answer to part C. And I'm going to have to scroll up here. C, my answer was an I9. So I want to multiply by I9. And then multiply all that by the square root of 1 plus 1 divided by my sample size, which is 12, plus, and now I'm going to do the value I'm trying to plug in, which is 90,000. We're plugging 90,000 in our advertising, minus the mean of our X value. So I have that here in M28. That whole value squared. And so I put that whole thing in parentheses just to be safe, because I'm dividing that whole thing by n minus 1, which is going to be 11. And then this is the variance here, the standard deviation squared's variance, and that's what else we found here. So 11 multiplied by M27. All right, and so now close out the parentheses for the square root. And when I hit enter, that is my margin of error. So just like every confidence interval we ever built, our point estimate, which we plugged 90 into our equation, got our estimate, that goes in the middle. So P22, if we add our margin of error, we get the upper limit. And if we take our point estimate and minus our margin of error, that is our lower limit. So we are 90% confident that if we spend 90,000 on our advertising, our sales revenue is going to be in between one of those two values, somewhere within that range. 16.2 is going to be pretty similar, just with some different values. There is one extra step here now in part E. Part D, again, is just like what we just did. You predict a confidence interval for if someone watches 30 hours of television. Now E here is estimate the mean number of pounds for all children who watch 30 hours. The steps are almost exactly the same. There's just one little switch up in the formula. Here's what we just did, the formula, and if you're doing the confidence interval for a mean or an expected value for everybody who would have that same X value, you use almost the identical formula. There's just no 1 in here. So same formula, just make sure you're using, or almost the same formula, just make sure you don't put, I'll show you again the old one, don't have that 1 plus at the beginning. And what that does is it's going to make a smaller value because you're not adding that 1 in there. And so I've made a note of that here. What I wrote, your answer should be a narrower interval, because when we're finding a confidence interval for a mean, we have more data we're working with. The mean should be more precise, so we end up with a narrower interval if we use that correct formula and don't have the 1 plus in there. 16.3 is going to be more the same, answering the same parts. And 16.4, I'm again asking you to skip a few of those in the middle. There's quite a few parts. It'll be okay if we skip E, F, and G. But other than that, it's exactly like what I just showed in this video. It also, like 16.2, has you do 2 confidence intervals, 1 with each formula. So let me jump back to my example quick. If I wanted to do that extra part and do the formula without the 1 plus, I can just take what I have here and just delete the 1 plus, and so then I would have the very next part of the problem. I get a narrower margin of error, and my upper and lower limits would adjust to be smaller.